So good evening. I'm Björn Enquist, and it's my honor and great pleasure to introduce the last plenary speaker, Alfio Quarteroni. He started his career in Pavia, education, early research, and then he's moved around. He's been professor in the University of Minnesota, Minneapolis, and now he has a chair in modeling and scientific computing at EPFL, École Polytechnique in Lausanne. He's also a professor in numerical analysis in Politecnico in Milano. The research field of Alfio is numerical analysis of partial differential equations. He has a rich body of work stretching from fundamental results in finite element, in spectral methods, domain decomposition, and he has applied that to a variety of different fields. So one field is what we will hear about, physiology. And there is another example, for example, it could be optimal design of sailboats. I assume that's why he has an honorary doctorate in naval engineering. Today's talk will be cardiovascular mathematics. Alfio, please.
So thank you very much, Professor Enquist. I'd like to thank the Scientific Committee for inviting me here. It's a great honor. So I'll talk about the cardiovascular mathematics. And the problem that we want to face is how to set up a mathematical model to carry out the analysis of the cardiovascular system, the circulatory system, which is made of arteries and veins and, of course, the heart. Now, when you face a problem from applications, you basically want to set up a mathematical model from one side. But then we also need to compare the results of our mathematical model with actual experimental data to make sure that what you are computing is meaningful. So the mathematical model has to start from a geometry. The geometry of, for instance, an artery that you want to analyze. Then you need equations that describe the physics that you are considering, and these equations very often are based on partial differential equations. Then you have to carry out the analysis of these equations because you want to make sure that the system is well posed, for instance. Quite obviously, you have to use numerical methods because the partial differential equations do not have a closed form solution. So you need to set up a method that allows you to go to a computer to solve the problem and to see results. And once you have these results, which may have a very complex form, you need to post-process them. You need to visualize, to represent them, in order that they could be, from one side, comparable with experimental results, and from the other side, that can be shown to your counterpart, say the doctor or a clinician. So a very important part is the comparison or the assessment. And when you compare results in this business, you have a different kind of data. You have in vivo, which are obtained from investigating a real patient, hopefully by non-invasive techniques, or in vitro that you can construct, that you can get by constructing some manufacts which represent arteries, for instance, and then you can compute fluid dynamics, you can run fluid dynamics inside this manufacts, and trying to end up with results which are similar to those that you could hopefully have in a real patient. Or otherwise, you have to resort to results from the literature. So if the results of your model are satisfactory, if they compare successfully, then on a variety of cases, then you're happy and you think that your model is correct. Otherwise, you have to iterate, and you iterate again and again, and very often, before having a reliable model, you have to iterate very many times. Now, this picture can provide a paradigm of many other applications, not only this one that I'm going to describe to medicine, but many other applications in classical fields of engineering or physics, say, or chemistry. But the extra difficulty here is that the data that you want to use are data which are provided by real patients. So you have data that you get from medical investigation and sometimes, or often, say, or almost always, these data are uncertain. So you have to filter them. You have to regularize them. You have to carry out a statistical analysis beforehand in order to make sure that you are using with data which are enough correct to carry out your model, say. So the first step is the geometric preprocessing. And geometric preprocessing consists of extracting 3D images from medical images, 3D geometrical models from 3D images, where you are going to solve the partial differential equation. So you need a computational domain where to solve the equation. You need statistical analysis to classify this data according to clinical protocols. You need to understand which kind of patient you are considering, you are treating, and then you need boundary and initial conditions for the mathematical model. So boundary conditions are needed because although the system is virtually infinite, it's not infinite, but it's basically infinite because it's made of so many pieces, you are actually considering a single part of it, and you need inflow and outflow conditions, and you have to generate these inflow and outflow conditions by clinical data, say. You also need initial conditions. You are starting evaluating the physiology of a patient from a specific time, and then you need to set up your initial solution. And then before going to the computational solution, you need to generate a computational mesh for surfaces and for volumes for 2D and 3D cases, say. So I'll go through these different pieces before showing the equation, say. So you start from a patient. You can perform magnetic resonance or a CT scan or digital angiography. In the case of magnetic resonance, you have a stack of images. The distance is 1 millimeter, one from the other, say. From these data, which represent a carotid artery. The carotid artery is the main artery that we have in our neck, and is responsible for bringing blood to our brain. Then from this stack of data, you have to construct little curves over every section. So you can do it in many different ways. You have to extract contours by segmentation, and in our case, you use B-splines to generate this little curve, say. Then you have to sample these curves by points, and these are very critical. So you have to end up with a sequence of points sitting on two-dimensional curves before generating the grid. Now, the surface, which is the external surface of an artery, for instance, is defined, for instance, by an implicit definition, by the level set of a curve phi, say. And phi typically is represented by radial basis expansion. So phi of x is the sum of certain weight time radial functions, which depends on the distance from the sample point. And the radial functions can have different forms. They can be phi of r equal to r, that's the linear case, or most often this is phi of r equal to r to the power 3. Now, we need to extract information from this surface, and in particular what we need is this normalized Hessian. We normalize it with the modulus of the gradient, because when you look at the spectral analysis, when you carry out the spectral analysis of this normalized Hessian, then you have the minimum curvature and the maximum curvature of the surface. And this is what you actually use when you have to generate the grid. So we have these curves, and we have to generate a grid. This is a preliminary grid made of little triangles that you put on the surface. And here we use the marching cube algorithm that was proposed by Blumenthal in 1994. It's a very fast and efficient algorithm, but unfortunately you cannot control the quality of the grid. You cannot control the acuteness of the angles, the regularity of the triangles. So you need some kind of optimization procedure in order to optimize the grid. And here is the actual grid that we are going to use. Once you have this grid, this is a superficial grid. You actually want to solve the flow equations inside the domain, inside the artery. So we need to construct a three-dimensional grid. So this is our carotid artery. This is a piece of the three-dimensional grid that you have inside. And this is already a numerical simulation. We have this three-dimensional domain. You can solve the equations on this grid, and you can have, for instance, this pressure pulse that is generated by the systolic, diastolic activity of the heart. So this is the preprocessing. You have to end up with a domain that is suitable to be treated, and in that domain, you want to solve the partial differential equations. And you need a grid which is representative of the actual complex geometry of the domain, say. Now we come to the mathematical model, which is the most essential part of my talk. The mathematical model, you need first of all to identify the relevant parameters. You have to study a problem on a specific patient, and you want to see which are the parameters that most importantly affect the type of solution that you're going to have. So blood viscosity, blood density, and more generally rheological properties of the vessel wall, of the arterial wall, say. Then you need to set up the partial differential equations, and this would be based on conservation laws, say. And then you have to carry out the analysis and set up the numerical methods. And you care about the stability, the efficiency, and the accuracy of the methods. You want a method which is stable, which means that it depends smoothly, regularly on the data, in particular on the numerical data, the grid spacing and the time spacing, say, the time step, which is efficient to allow you to obtain the solution in a reasonable time, not to wait for months, to wait for days, or hopefully to wait for hours. I'm not saying minutes because these are quite complex problems, and accurate enough to make sure that eventually you have a solution that resembles the real solution, the physical solution, say. Then you have to go to a computer, to use a computer to carry out the simulation. And for many problems, you have a control to activate because you want to control the actual form, for instance, of a surgery, of a bypass, or a shunt, or a stent, as we shall see, in order to make sure that the results, the final results, are optimal in a suitable metric, say. Clinically optimal, of course. So, I'm going to talk about the local flow analysis, what happens in a single artery, what happens concerning the interaction between the flow field and the deformation of the artery, and this is the fluid structure interaction. What should we do when we want to look at the problem in its entirety, going from a single artery to the whole set of arteries in the cardiovascular system, and this is geometric multiscale, and then try to see to which extent we are far enough, we're far from the complete understanding of what is going on in our body, say. So local flow analysis, this is the global system that we like to work on. Blood is not, strictly speaking, a fluid. It's rather a suspension of red cells or erythrocytes, leukocytes or white cells, and platelets, or the liquid which is called plasma. So this is the entire system. It's a simplified picture of the entire system. That's too complicated. So we want to go to a local level. Go, for instance, to the local circulation between the heart and the lungs for the oxygenation of heart, and then sticking with a specific part, which is a specific part of an artery, a single artery, say. So we want to concentrate on a single artery in a truncated artery. The first thing to decide is which kind of representation we'd like to use. As you know, in a partial differential equation, continuum mechanics, you have at least two different kinds of representation, the Lagrangian and the Eulerian. The Lagrangian, you follow gold particles, but this is unsuitable for this problem because if a particle which is sitting somewhere in the aorta, ascending aorta, you follow its displacement, then you are forced to follow it all along the complex pattern of the cardiovascular system. So this is not the right approach for this problem. You could rather use the Eulerian representation. You fix a specific domain and you just go through this window and see what happens in this specific domain. The problem is that you are missing the deformation of the arteries in this case. So not suitable either. And indeed what you do is using this so-called arbitrary Lagrangian Eulerian, or ALE. With the ALE, you target a specific domain, an artery with an inflow and an outflow, but to allow this artery to deform, because you actually want to compute the change of energy between the fluid and the artery, the vessel deformation. And it is called arbitrary Lagrangian Eulerian because actually it combines the Eulerian approach for fluids with the Lagrangian approach for the vessel deformation. And not only that, it's called arbitrary because you have to retrieve at each time the actual form of the computational domain, which is a 3D volume, and for that you only need the shape of the surface. So you have an arbitrarity in reconstructing the shape of the volume moving from the shape of the surface. This is why we call it ALE. In a very synthetic form and after form, you may think of having a global domain omega hat at a reference time. This is the whole cardiovascular system, say, and we target a specific domain, omega hat F, where there is the fluid, for instance, a single artery. And then you have this Lagrangian transformation that gives you the domain omega T, which is the complete cardiovascular system at time T, but you have the arbitrary Lagrangian Eulerian, the ALE map, that retrieves you the actual form of the computational domain at the given time T. And what we need is the derivative of the deformation, is the rate of the deformation of this AT, and we call it W hat. So W hat is a crucial velocity that will enter the Navier-Stokes equations to model our system, say. So this is the Navier-Stokes, these are the Navier-Stokes equations for our problem. So in a very simplified manner, this is our omega F of T. This is a branch, a bifurcating artery. We have plenty of bifurcation in our body. We start from a single artery, which is the aorta, and then you have at least 14 levels of bifurcation in the whole, so 14 different levels in the whole body. We truncate this domain artificially, so we have an inflow boundary, gamma D, where we put a Dirichlet data, and an outflow boundary, gamma N, where we put a Neumann data. And then we have gamma of T, which is a critical part, because gamma of T is actually the surface of the domain which is deforming. So if it were fixed, you would have a Dirichlet homogeneous boundary condition there. But this is not the case, so we'll see that we have to couple this with an actual deformation law for the wall. So we have the assumption that is true in the heart and in large arteries, that the flow is homogeneous and Newtonian. So the viscosity is constant, which is not true in the capillaries, as we shall see later on. We use the Cauchy stress for the fluid, sigma F, which is the classical form of Newtonian Navier-Stokes equations. And then we have a strain rate tensor, and the incompressible Navier-Stokes equations in the ALE form are here. So what you see is from one side the momentum equation, where you have some extra terms which are due to the ALE map. In particular, you have this ALE velocity field that I was talking about before. You have the continuity equation, and then you have Dirichlet data and Neumann data on the inflow and outflow boundaries, which are artificial. And finally, you have that UF, the velocity field, is equal to U gamma on gamma, and gamma is the deformable domain. So we need an extra equation for gamma. This is an example. This is a solution in a rigid domain, so rigid boundary. And here you simply see the velocity profiles, different sections. And you see that since the inflow is time-dependent because of the pulsatility of the heart, you see that you have flow reversal, which poses some difficulties in the analysis of Navier-Stokes equations, because at the outflow actually is not an outflow. You have the section where the integral of the normal component of the velocity field is, of course, positive, but you have flow reversal, which is critical. And this is physiological. Why is mathematics so important in this business? Well, 15 years ago, some medical doctors in the US discovered the correlation between this quantity, which is called wall shear stress, and the rise of atherosclerotic plaques in arteries, so occlusional arteries. So wall shear stress is something that you can easily get from the Navier-Stokes equations as a post-processing step, but it's something which is very difficult to measure in the clinical practice. And here you see two examples. This is a congenital heart disease. in neonates. And here is on the coronary arteries. This is the distribution of the shear stress. So the wall shear stress. In particular, what is considered to be dangerous is a wall shear stress which is low with respect to the physiological values and which is highly oscillating in time. So low, it's small, but highly oscillating in time. This is the best case. So you are interested in looking to this kind of dynamics in time of wall shear stress. And with Navier-Stokes equations, this is something that you can, I would not say easily achieve, but you can achieve if you have a good solver for Navier-Stokes equations in this domain. So, as was said before, blood is not really a Newtonian fluid because of different kind of phenomena that occur in the arterial system, say. One of those is the so-called rouleau aggregation. So the red blood cells aggregate as in many stack of coins, as you see here on the left-hand part of the picture. Besides, you have the so-called Farreus-Lindquist effect, which occurs in small vessels, where red blood cells move toward the central part of the vessel, and the blood viscosity shifts toward plasma viscosity, which is much lower. So the viscosity is not constant anymore. So you have to account for this variation of the viscosity. And of course, it depends, in general, non-linearly from the flow equations. So this is the standard Navier-Stokes Newtonian Cauchy stress, say. And there are several models that try to account for this dependence of the viscosity on the velocity field, and more specifically on the rate of deformation, or the shear rate, which is called gamma dot. This is a classical conventional notation, say. And gamma dot is up to a certain multiple, the square root of the trace of the square of the rate deformation, say. The most classical model is a called power law model. So mu of gamma dot is simply proportional to gamma dot to the power n minus 1, and then is a critical exponent. If n is less than 1, which is somehow accepted by everybody, then you have a decreasing function of gamma dot, as you see here. These are different values of the different behaviors of the curves for different values of n and k, and you get a shear thinning fluid, and it's somehow understood that the blood in small vessels should behave as a shear thinning fluid. But there are more sophisticated models. Here is just a list of those: the Powell-Eyring, the Cross, the modified Cross, the Karo-Yasuda, and they are all function of, in all of them, you have that mu of gamma dot minus mu infinity over mu zero minus mu infinity, where these are constants that you can get from the blood analysis, say. Then these are nonlinear functions depending upon critical values of lambda and dem, which are material constants for blood. So this is far from being the final word on these models. People are still working to provide more convincing or more effective models to describe blood flow in small arteries, in small capillaries, as non-Newtonian fluids, say. The vessel wall deforms. It deforms under the action of the heart, and it deforms because it has to store energy during the systolic phase and return energy to the blood during the diastolic phase. Systolic is the compression of the ventricle, diastolic is the dilation of the ventricle cell. So, first of all, you have to develop a model for the vessel wall, and then to consider the coupled system between the fluid and the vessel deformation, say. So this is the mechanical interaction between the fluid and the vessel, but is not the only important interaction between the fluid and vessel. We should also account for biochemical interactions, and this is regulating the different kind of mass transfer processes that you may have. You have macromolecules like cholesterol, for instance, passing from the lumen to the vessel wall. You have drug delivery when you take drugs, and you have the dynamic of oxygen. So what you see here is just an example of the oxygen solution in the heart, in a lumen, and then you have to set up suitable interface problems to allow this oxygen or these macromolecules to go from the lumen to the different layers of the artery cell. So you have nonlinear Kadam-Kachowski-like equations to describe the flux across the different layers. I will not talk about that in this talk, I will stick on the mechanical interaction. And first of all, what you need is a model for the vessel deformation. And here, again, there is not a general consensus. There are several models that are proposed, and some of them are also very simple, oversimple, like one-dimensional models, and very often bioengineers use zero-dimensional models, just algebraic laws. Here, what we use is a three-dimensional model. Of course, we use a Lagrangian approach, which is more suitable. So you describe the deformation from an initial state. You need a deformation gradient, and you have this rho hat, which is the density in the reference configuration, the density of the arterial wall in the reference configuration. The deformation gradient F hat, the Jacobian, the second Piola-Kirchhoff tensor, and this sigma hat, which is obtained from a density of elastic energy, and you take the derivative of W hat with respect to Green-Lagrange strain tensors. I think this is quite classical. Of course, what is difficult is characterize the different rheological behavior that you want to consider in this case. And this is the global problem that we have actually to solve if you want to retrieve the solution of the coupled fluid structure problem. So we have three components. Two of them are obvious. We have, you see, Navier-Stokes that we already seen, the blue equations, the equation for the structure, and then you have some red terms which are responsible for the coupling. First of all, there is an extra guest here, which is the geometry. Geometry is an unknown of the problem. You have to deform your problem. You have to deform your domain. And for that, you need, first of all, to compute the deformation of the surface, and then the deformation of the surface on the interface between the fluid and the vessel, and then you have to extend it, for instance, by an harmonic operator, or by an elastic operator, or by a Stokes operator, to get a deformation inside the domain in order to compute this famous ALE velocity field. This is the arbitrarity. You can use any kind of extension operator here, and the solution at the end will not depend on let's say, the Z solution will not depend on this. The numerical solution, of course, would depend on that. Then you have the actual form of the problem, of the domain, omega f of t, and then you have two equations, two red equations. UF equal to W, which is a kinetic condition. You are just stating that blood particles that are hitting the endothelium surface, they have to move according to the deformation law of the wall, say. So there is no cavitation, there is no empty space, fortunately. And you have an extra equation, which is a kinematic equation, which states that the forces should be in equilibrium. So this is a kind of action-reaction principle. The energy which is transferred from the blood to the artery is returned from the artery, from the vessel wall to the blood cell. So this is the global system that you have to solve. And here are some references. There are very many people who have been working on those kind of problems, not necessarily on the application to blood flow, but whose results are somehow relevant to this type of application, say. So let me quote the paper by Letal and Moreau on the ALE formulation, the paper by Berauda Vega on the existence of a simplified model of fluid structure interaction, and on the same line, paper by Desjardins and Estebanos, Puel, Ramon and Madé on existence results for fluid structure problems, even though not necessarily applied to this specific kind of example. And then techniques used by Jacques Libiance and Zhuazhua, Zhang and Zhuazhua on control Then other papers by Murray and Vasquez and Chen, Kutar, and Scholar on generalized Stokes problem for this type of applications on moving domain. Paper by Formaggio, Nobile, and Boff and Gastaldi on the stability of time-dependent approximation of problems in moving domain. So there is a lot of work that has been done, and there is much more work that is still to be done to come out with a complete analysis of the previous system set. So this is the way we treat it numerically. We want, first of all, to see the whole problem as an interface problem. Roughly speaking, we go from 3 dimensions to 2 dimensions. We work on a 2-dimensional manifold which is the endothelial surface. So this is a sketch of the situation. This is a 2-dimensional section, vertical section. You have the blood flow here. You have the structural equation in the blue part. And then you have a tiny region, the yellow one, which is the interface. This is the endothelial interface. So can we reformulate the whole problem as a problem living only on the interface? And we do it through the so-called Stekel-Poincare equation, where we have an operator equation, which is made of 2 pieces, the Stekel-Poincare of the fluid and the Stekel-Poincare of the solid, which is the arterial wall, say. Lambda is the displacement of the arterial wall, which is the unknown. And to construct it in a very formal manner, we proceed like this. Assume that we know this deformation of the arterial wall. You solve the Navier-Stokes equations, U and P, and this is the resolvent in the fluid part. Then you compute the normal stresses, Cauchy stresses, and this is the Stekel-Poincare form in the fluid part. So basically it's a Dirichlet to Neumann map, which is nonlinear in this case. You do the same for the structure. You move from lambda, which is displacement, you compute the solution of the structural equation, and then you compute the stresses, the Cauchy stresses for the structural part. And you have these 2 basic components, the Cauchy stresses of the structural part and the fluid part. You have to equate them for the kinematic equation, and you end up with this Stekel-Poincare equation. Now we have to solve it. So far we have only been reformulating the problem as if it were a problem only on the interface. Now we have to solve it. To solve it, use an iterative method. Let's say a classical gradient method, for instance, where we compute the slope, and we compute the residual, and you have to precondition the residual, and this is the critical part. If you don't precondition, you have a very ill-posed problem. You have a very ill-conditioned problem. The spectrum of this operator is fairly big, numerically speaking, and you will never be able to end up with a convergence procedure. So you have to precondition, and this is the way we precondition it. We take the linearization of the Stekel-Poincare for the fluid and the Stekel-Poincare for the structure, and we take the inverses and we sum up the inverses, and we weight them by suitable weights. And this is the inverse of our operator. So roughly speaking, at every step, we have to solve independently a fluid problem from one side and the structural problem from the other side, and recombine the 2 stresses that we have and proceed according to this conjugate gradient method set. So this is a solution that you get after solving this problem. This is a carotid bifurcation, and here is the deformation of the vessel wall under the action of the systolic, diastolic phase, say. And this is the same solution, but now you see not only the deformation of the wall, but also the flow problem. So the colors refer to the different values, to the intensity of the flow of the vector field, and arrows indicate the vector, say the velocity vector. So it seems good, but indeed there is a major problem here, and the problem is due to the back reflection of the pulse wave. So you see here, this is a section of a cylindrical artery. We just break it down to its half part just for the purpose of representing the results. And what you see here is that there is a very strong back reflection, which is due to the fact that this treatment of the outflow is not mathematically correct. First of all, this outflow is not a physical outflow, it's an artificial outflow that we put to solve our problem. And then we have solved it by using a free stress condition, Neumann condition, for the fluid part, and absorbing boundary conditions for the vessel part. This is an astrodynamic system, so it's a hyperbolic equation, but this is not enough to prevent these waves to be reflected back. So we are solving an incompressible fluid equation, but yet we have a reflection because of the pulsatile nature, because of the fact that the domain is deforming itself. So how to cure this? Now, to do that, you have at least two ways. Either you resort with smarter boundary conditions, which is not easy, or you try to see these as part of the old system. So embedding these in a more general picture and trying to see how it behaves when it's part of the whole story. So this is why we developed the geometric multiscale, which is due to the fact that, which is motivated by the fact that the circulatory system is a complex one made of the heart, of the small circulation or the global circulation. You have different pieces that are acting in a different manner. And the fluid dynamics features of the different pieces and also the structural features are completely different. The Reynolds number is 3,400 in the aorta. These are indicative numbers. And is 0.002 in the capillaries. So, first of all, the flow is not turbulent unless in some specific conditions. It might be turbulent in stenosis, or it might be turbulent when you have low blood density, like in anemia or in other blood diseases. So you have a plurality of situations, and you have very many pieces because you have a single aorta, but you have as many as 3 times 10 to the power 9, so 3 billions of capillaries, say. So how to keep track of the whole story? So here comes the geometric multiscale help. We like to solve the problem in a specific domain like this one, but indeed we want to see it as part of the global nature. And we go to the global level 2, where you have very few arteries and very few veins, the most important one. And then we go to a global level 3, where you have the capillaries. So we start from a specific environment when you want to solve the local three-dimensional, and then we would like to go to a level where we privilege the most important arteries and veins, and then go down to the 0 level, where we have the 3rd level, where we have a capillary network. And the problem is that here we use Navier-Stokes in three-dimensional domains. Here we want to use one-dimensional Euler system, and here we want to use 0-dimensional ordinary differential equations. So this is the geometric multiscale stuff. And this is the way it works in a, let's say, in a sketchy form. This is 3D. If you have a bifurcation, of course, you have to go to the 3D. Now here, when you have straight cylinders, you may want to use 1D, and this will be based on Euler equation. And here, when you have capillaries, we would like to regard them as being analogs of electrical circuits, because in that case, we will be able to use ordinary differential equations, system of ordinary differential equations. So we go from 3D to 1D to 0D. You can carry out this type of simplification according to different strategies, mathematical strategies. One way is to use asymptotic analysis, making some assumptions on the physical behavior in, for instance, in these blue parts, and then you end up with a system that is virtually the Euler system with some extra dissipative terms, say. You can do more. You can linearize, consider all the average quantities, and in that case, you obtain 0-dimensional systems, ordinary differential equations. And to do that, you have to keep in mind that you are somehow assimilating the flow field to electrical circuits. And here is the dictionary. See, the pressure as a fluid dynamics quantity is the equivalent of voltage. The flow rate of current, blood viscosity of resistance, blood inertia as inductance, and wall compliance as capacitance. And in this case, you are able to describe the behavior of a very complex network of capillaries, for instance, as a system of electrical circuit. Now, what can you simulate with these reduced systems? This is the one-dimensional. With one-dimensional, you can easily simulate single pieces of arteries, cylindrical, accounting also for narrowing, say. You can do junctions, like in this stented abdominal aorta. So if you If you join different pieces, like in a Lego, then you can use one-dimensional models to account for propagation of waves. But you can do much more, actually. You can account for this complex system of 55 arteries, which are the most important arteries. These are those that you have seen in the previous picture, the red arteries, say. And you can solve your network of Euler equations in this set of problems and have a global picture of the circulation. You can go at a lower scale, the zero-dimensional scale, to divide the whole body into compartments, to set up electrical circuits for the compartments, which ends up with a system of ordinary differential equations, actually differential algebraic equations. And if you solve this, you can compute the solution in the peripheral part of the body. So, once again, the idea is to embed a two-dimensional or three-dimensional system, for instance, a bifurcation or a coronary bypass, then prolongate it with one-dimensional models here and there, and then embed it in a big map of zero-dimensional networks, like in this simple case, where you see that you have a complete picture. Here we're just taking the pressure at some specific places, but this is part of the old system, and here is a two-dimensional coronary bypass, which is solved by Navier-Stokes, and the inflow and the outflows is generated by this global 1D and zero-dimensional system. And there is a feedback mechanism, so the system is actually coupled. By this manner, we cure these pathological, let's say, back reflections that we had in the single system, like in this case. Here is a 3D cylindrical vessel with a 1D extension, and you see that waves, the pressure pulse, propagates safely through the one-dimensional extension, say. So here is a coupling of 3D and 1D. This is a 3D in a bifurcating channel. This is a carotid artery. There is a 1D extension that you don't see here, but is there, and you don't have spurious back reflection, say. And you see, for the same problem here, the pressure wave, you have this one-dimensional extension. There's another one here which is not reported for graphical purposes, but you see here is leaving the domain and going through the one-dimensional system to the rest of the bodies. A few references. First of all, I think it's important to mention that the first paper is the one from Euler, Leonhard Euler, who actually provided his system of Euler, which is so popular in aerodynamics, for instance, gas dynamics, on the occasion of his investigation of blood flow in one-dimensional vessels, say. Then you have a series of papers where it's dealing with the continuous dependence of 1D system from the data, existence of local in time regular solution in half space for 1D by Čenić, Kim, and Mikelic, asymptotic analysis for 1D zero decoupling, existence of regular global solutions on boundary domains without source term and special boundary conditions, and treatment of interfaces, because you have to set up suitable models to have the different models interact one another, the 3D with the 1D and the 1D with the 0D. And here we use either Lagrange multipliers or optimal control to account for this interface treatment. This is already a substantial part of the investigation, but it's only a piece of the whole investigation, because what we have been doing so far is concentrating on circulation model. We actually have models for the heart that have not shown here, but this is the kernel of the investigation. Now, to be more realistic, one should also add the nervous system, the ureteric compartment, like the spline check system, and the respiratory system. And then, since we're not talking about inanimated structures, but we're talking about living people, you have to account for the metabolism, the way the body reacts to the specific physiology or to the specific extra condition. In particular, the metabolism that we have developed only in part should be capable of account for the chemoreflex effect and the baroreflex effect that have a very strong impact on the circulation model. If you try to investigate the behavior of blood in people like you now at rest, you find completely different picture than on athletes or people who are under severe conditions, say. The final part is post-processing and model validation. Did you work correctly? So far we have seen plenty of mathematical equations, but now we'd like to see whether with this equation we can try to solve some problems which are considered to be relevant for doctors, for instance. Now, let me mention again the mathematical aspects here. The first one is to develop an error analysis. We like to compare with an exact solution that you seldom have, of course, but sometimes you have an exact solution of a simplified problem, or compare with benchmark problems or other results. Comparison with experimental results, in vivo or in vitro, and then having the final assessment by medical doctors and clinicians. And I'm not going to give any dogmatic presentation in this respect, namely to end up with a series of tests that one has to pass in order to convince the doctors that the model is correct. I'm simply mentioning 3 different kind of applications that were suggested to us by doctors, and in which we can hopefully see the potential of these tools in order to solve specific problems. The first one is cavopulmonary shunt for congenital heart disease. The second one is on cerebral aneurysms, and the third one is on stents for occluded arteries, say. The cavopulmonary shunt is a collaboration with the Great Ormond Street Hospital in London and the Laboratory of Biological Structure of the Polytechnic of Milan and the Cariplo Foundation, which is the sponsor of this work. And here the problem is that may have, unfortunately, children who have only one ventricle. So for them, it would not be possible to establish the small circulation between the ventricles, the heart, and the lungs. So the blood could not be oxygenated, and there is no chance for these neonates to survive, unless this pathology is detected at a very early stage in the fetus, and then they are immediately operated. So here are 2 clinical surgical approaches. The first one is the so-called sentinel shunt. One has to create a bridge between the ascending aorta. Heart is somewhere here, okay? So this is the ascending aorta and the right pulmonary artery. So we're just sucking blood from the aorta to bring it to the lungs. And here is another operation. They are both used every day in very specialized places. That's the second operation. You take now the blood from the innominated artery and not from the ascending aorta. So this is the modified blood toxic shunt, and this is the central shunt. So the obvious question is which one performs better. And as you can imagine, this is a fluid dynamics problem. The second question is the following one. Assuming that it is clear that one is better than the other, how can you shape this CS or MBTS in an optimal way in order to make sure that not only you oxygenate the blood, but you make sure that you keep iterating the other parts of the body, the brain, the coronaries, the lower part of the body. So you have to end up with a kind of flow conservation and to flow redistribution of blood, and in order to guarantee that all vital processes in our body would keep working properly. So as macroscopical elements of decision for the clinician, there is the choice of the radius of the shunt, and make sure that the balance is correct, and that the coronary flux is kept at the right level. This is our computational domain, our omega f, which is deforming in time, so it's omega f of t. But the problem here is that this omega f, this mathematical omega f, has plenty of inflow and outflow boundaries, which are virtual boundaries. How do we provide data to these virtual boundaries? There is no way to provide data to a virtual boundary in an exact form. So there is no way to guess which kind of inflow and outflow condition you can put there to be respectful of the actual nature of the problem. You know, if you work in fluid dynamics, how far the solution of Navier-Stokes equation is sensitive to the inflow and outflow boundary conditions, and of course also to the geometry. So we have embedded this system, this shunt, in our geometric multiscale problem. This is the shunt. This is the global zero-dimensional system to describe the rest of the circulation. So here is an interaction between a 3D and a 0D system. 3D Navier-Stokes with a system of differential algebraic equations. And in this way, you don't need to force boundary conditions. Boundary conditions come automatically from the external environment, and it's not only an inflow point here, it's a feedback mechanism. So the shunt is providing conditions also to the ordinary differential equation system. And we are very proud of this type of investigation because for the first time, a numerical solver was able to see that in the shunt there is flow reversal that was observed by the doctors, by the surgeons, but was never reproduced before due to the mistreatment of boundary conditions. So now we can better shape the form of the shunt since we have more reliable physical data to compare, mathematical data to compare with. This is the second application, and has to see with cerebral aneurysms. Now, this time, the main body is the Niguarda Hospital in Milan, which is perhaps the most important hospital in Italy for the cure, the treatment of cerebral aneurysms. And Siemens is the main sponsor of this project, say. So cerebral aneurysms are lesions arising on the brain. What you see here is the brain from the lower part. And you see this so-called circle of Willis, which is sketched here. The circle of Willis is there to dispatch and to distribute the blood that is coming from the internal carotid artery to the brain. So it has, of course, a vital importance. And this is a very smart system because it can self-adjust, even in those cases where you may have an occlusion on a specific piece. So quite often the aneurysms are subject to rupture, and in that case you may have dangerous cerebral hemorrhagia, say. And it's estimated that 5% of the population has some type of aneurysms in the brain, and they are completely asymptomatic. So in general, there is no way of deciding or understanding or monitoring them if you are not undergoing a specific clinical investigation, say. The project wanted to highlight the role of the vascular morphology with the correlation between the vascular morphology and the risk of presence of development of cerebral aneurysm, say. And the method that was used is a merging of statistical investigation and numerical investigation, numerical simulation, to end up with some results which could provide doctors with a better understanding, say. So this is the geometrical preprocessing. This is a arterial vessel in a real patient. We have been working on 65 real patients, and it's very difficult to have real data from patients. These are in vivo data, and they're very difficult to get. So there are several ways to characterize morphologically this three-dimensional domain, say, by center lines. Then we look at the radius of the maximally inscribed sphere. We want to identify each bifurcation. we have to compute this to retrieve the central lines of each branch, and then to identify the branches. So this is the pre-processing that you have to carry out in order to make sure that you are working with, you can classify the kind of patient or the kind of aneurysm that you have. This is an aneurysm that you have, this enlargement of the artery, say. This is reconstructed by geometrical data. This is the pressure field after the numerical simulation, and these are the velocity streamlines of a single aneurysm, and this is the way you can track the particles in the aneurysm. And one very important parameter here is the residence time in the aneurysmatic sac. And the doctors are very happy to have a quantitative tool to compute the residence time in this part, because this provides an indirect measure of the capability of the flow field to exert resistance or wash stress on the surface and eventually to create rupture, say. This is one element of investigation. And this is what you can get, and this is a quite, to us, surprising result and useful result, because on the basis of this observation, what we have seen is that aneurysms do not distribute randomly. They tend to prefer two specific sites, and these sites are just downstream the regions of maximal curvature of the internal carotid artery. So it seems that there is potentially a very clear correlation between the fluid dynamics behavior and which is affected by the structure of the curvature of the vessel wall and the presence of aneurysms. And on the basis of these results, now doctors at the Niguarda Hospital are investigating clinically their patients and try to see if there is a precise feedback or confirmation to this type of conjecture, say. I'm going to conclude. I think I have still a few minutes, 5 minutes, maybe 3 minutes, okay, by talking about a third project. This is due to the drug-eluting stent. So what is a stent? Is a network, metallic network that you put in an artery to restore the flux or to restore the lumen, say. You have a narrowing and you insert this balloon, you inflate the balloon, and this is inflating the stent, say, and the stent then is deployed, and it's there to restore the original lumen, say. So stents have a very strong interaction with the endothelium of the vessel wall, and actually they are recognized as external body, or and they are cannibalized actually by production of endothelial cells over few months. So in the new stent technology, the industry tend to use a coating of heparin or other inflammatory substances. So the new stents have a coating with an anti-inflammatory drug, which is released. And this is a kind of multiscale problem because you're working with different scale. The scale of the wall thickness, which is of the order 1 millimeter, and the scale of the thickness, which is 5 micrometers, say. And you have 3 phases. The effective solid phase where the drug is bound to the polymer, to the coating. The virtual solid phase where the polymer is swelled. You have a free interface. And you have the liquid phase where the drug is dissolved in plasma. And we have a model to describe this at the micro scale for the let's say in the arterial wall. So it's a diffusion advection process. U is the velocity field which is provided by the Navier-Stokes equations. Then you have the liquid phase, the virtual solid phase, and the effective solid phase. And you have critical quantities that depend on the polymer characteristics, and they are determined by stochastic models. So you're trying to use a micro description based on the stochastic approach and a macro description based on differential equations, say. This is the numerical treatment. This is just a piece of a stent. This is the geometry around, the grid around. And only for this very simple piece of stent, you need almost 1 million of elements in the stent coating and 1 million of elements in the wall. And that's too much because you have very many components of this in a single stent. So we have to resort to a simplified process or simplified model. And actually, the coating is not considered as a three-dimensional body, but just as a place where you have to adjust the flux condition. So we're working, we have a model for the transient flux, and we avoid solving the problem in the coating. This is the numerical simulation. This is a drug release of heparin from our stent. And this is the blood plasma pressure. For a realistic model, this is a simplified model, this is a realistic model, and this is the way the stent expands and the drug is released. So a critical clinical problem here is that in modern stents, drug is released too quickly, in 1 day, about 24 hours, and that's too quick with respect to the proliferation, the critical time of proliferation of the endothelial cells. So the challenge today is to produce coatings that allow this release in a much smoother way, slower way. And you have several ways to do that. You can modify the form of the coating or creating multi-layers or modifying the form, the type of drug. And here is an example where you have two different approaches. This is a uniform coating, and after 1 day, the concentration has reached, basically after 2 days, has reached its steady state. That's too fast. And this is what is called a coffee cup stent coating, because you have 3 different layers, like a cup of coffee with 2 different interfaces, and this is released sequentially. And what you see is that after 3 days, the diffusion process is still working properly. And this is the challenge. Try to make this even slower in order to make sure that this effect of diffusion of heparin or other substances takes order of 4 or 5 weeks to be effective enough to contrast the release of the production of the proliferation of cells. So the conclusion is that I think this investigation, this kind of investigation, are useful to understand better the basic physiological processes, and this is basic research, after all, to assess the risk, to produce risk indicators for pathological surprises, and this is useful for the clinical diagnosis, and also to help developing therapeutic and surgical planning, and here optimization and control, and shape optimization and control has a lot to say. But even perhaps more important is that is a good opportunity to develop new mathematical tools that are suggested by the complex nature of the problem that we have to treat. Let me conclude by acknowledging the main bodies, MOX at Polytechnico Milan and the EPFL, with different players, and the many external collaborators that we are working on every day, and I would like to thank you very much for your kind attention.